Hello everyone, I'm Ryan Kozak, and my co-authors are Mandeep Jain, McClelland, Aaryaman Shah, and Professor Mohammad Zarifi. I'll be giving a presentation on a conference paper titled Durable Ice Sensors Utilizing Microwave SRRs Coated with a Protective Epoxy for De-Icing Control. Before I begin, I'd like to acknowledge the Silex Okanagan Nation for the use of their unceded territory, the land on which this research was conducted. The contents of this presentation will proceed as follows. I'll begin with a description for the motivation of this project. I'll then briefly discuss the operation of resonant microwave sensors and the electrical properties of water and ice. This will be followed with a demonstration of the SRR sensor operating with a protective epoxy coating applied to its surface to detect ice. Then I'll discuss the design and fabrication of a system-level implementation of a resonator sensor and readout circuit. And finally, I'll conclude this work and provide future work to be performed. So why are ice sensors needed? Undetected ice can create serious safety and efficiency concerns. For example, ice accretion on aircraft increases their aerodynamic stall speed and has directly resulted in catastrophes such as Air France Flight 447 and American Eagle Flight 4184. Furthermore, many large renewable energy companies, including RWE and ZED, have reported having accurate, real-time ice sensing could result in gains of up to $250,000 annually per wind farm site. Other applications of real-time planar ice sensors include characterization of anti-icing and de-icing technologies, implementation into pathways and roadways, increasing refrigeration efficiency, detection of ice on power transmission lines, and the list goes on. With the motivation for this project established, the microwave sensing technique we've used to implement these sensors will now be further explained. I'll begin with a brief description of how resonant microwave sensors function. When discussing resonant microwave sensors, I'm referring to devices which operate between 300 MHz and 300 GHz. The operation of these microwave sensors can be described with the help of Figure 3. In short, these sensors are capable of detecting and distinguishing between materials in their near field by interacting with the electrical properties such as dielectric constant and loss tangent. Figure 3 contains the resonant profile of a microwave resonator. This resonant structure acts as a narrow bandpass filter, resulting in a peak in the frequency spectrum with a resonant frequency and resonant amplitude defined at the maximum of that peak. When a material like ice or water is introduced onto the sensor, the electrical properties of the material interact with the incident wave and shift the resonant frequency and resonant amplitude. The different materials possess different electrical properties, resulting in the resonance shifting differently. This enables the capability to distinguish between materials on the sensor. In the case of water and ice, the difference in dielectric constant and loss tangent is extreme. At 5 GHz and 0 degrees Celsius, water and ice have dielectric constants of approximately 90 and 3.2, making the distinction between the two materials easy in the microwave spectrum. In Figure 5a, I've measured the dielectric constant and loss tangent of water at 4 different temperatures. These graphs clearly depict how the electrical properties of materials can vary over both temperature and frequency being considered. The permittivity properties of water and ice can be explained by the molecular structure of water as seen in Figure 5b. Due to asymmetric covalent bonding between oxygen and hydrogen, each water molecule can be modeled as an electric dipole. Additionally, Figure 5c displays how multiple water molecules interact. In liquid state, these molecules are freely able to move and slide between each other. However, once the water freezes to ice, the hydrogen bonding becomes more permanent and the molecule can no longer freely move or rotate. This directly results in the significant difference in permittivity between water and ice. When an electric field is passing through water in liquid state, it aligns the molecular dipoles, which are free to move, resulting in a high dielectric constant. When water freezes to ice, however, these molecules can no longer easily be reoriented by the electric field, and the permittivity reduces. The loss tangent of liquid water is high due to vibration damping, as the molecules continually oscillate in the changing electric field. Ice has a much lower loss simply because the molecules cannot freely move around. During the design process of the SRR, an operational frequency of 1.2 GHz was selected, and Rogers 5880 substrate with a relative permittivity of 2.2 and dielectric thickness of 0.79 mm was selected for design and fabrication. With the desired resonant frequency in mind, the half wavelength equations can be used to determine an approximate length of the ring. This length can be then further optimized through simulation to achieve the desired resonant frequency. The experimental setup constructed to analyze the ice sensor is seen in Figure 6. This setup was designed to perform cooling experiments using a Peltier cooling stage. The hot side of the Peltier device was water-cooled, allowing for cold side surface temperatures as low as negative 20 degrees Celsius. The response of the sensor was monitored using a portable FieldFox vector network analyzer, and while recording the results, the VNA was set to sweep 1,601 points over a frequency range of 0.9 to 1.5 gigahertz. For any industrial applications, the durability of the resonant structure needs to be improved. If we simply leave the copper layer exposed, it would rapidly deteriorate and change the resonant behavior. By coating the sensor in a protective epoxy layer, the durability could be significantly improved. The relative permittivity and loss tensions of the epoxy were measured using a dielectric probe kit and determined to be 2.6 and 0.003 respectively at 1 gigahertz and 24 degrees Celsius. For the purpose of this study, we will examine three scenarios: the uncoated sensor and the sensor coated in an epoxy layer with a thickness of 0.5 millimeters and 1 millimeter respectively. Upon fabrication of these sensors, the simulated and measured responses were compared in Figure 7. Some variation was expected due to soldering and the SMA connectors not being accounted for in the HFSS simulations. Following this validation, icing experiments were performed on all three sensors as seen in Figure 8. Observed in the results of Table 2, as the thickness of the protective epoxy coating increased, the change in resonant frequency decreased, which can be attributed to less fringing field interaction with the water or ice on the sensor. Resonant amplitude and resonant frequency were both determined to be excellent detection parameters, as both showed measurable and consistent changes in all three experiments. With the coating applied, the sensor still exhibits high interaction with the ice, validating the use of epoxy as a protective coating on the transmission lines. In order to implement this sensor into real-world applications, the use of a VNA should be eliminated to make this technique cost-effective. This can be achieved by monitoring the amplitude of a single predefined frequency passing through the SRR implemented using a voltage-controlled oscillator and power detector as shown in Figure 9a and b. The power detector converts the high-frequency AC signal output of the SRR to a DC signal. This DC signal is then further processed using differential and non-inverting amplifiers to enhance the dynamic range of the system. When tuning the readout circuit, I selected a frequency near the resonance when ice was on the sensor, however not exactly at the peak as shown by the dotted line in Figure 9c. This was done to reduce the sensitivity of the circuit to variance in the output of the VCO. The result of these experiments showed that the readout circuit could distinguish ice, water, and the bare sensor as seen in Table 3. This study indicated how a readout circuit could be implemented for microwave devices to be cost-effective for use in industrial ice detection applications. So in this study, we have validated epoxy-coated SRR sensors as highly durable ice sensors. We also designed and validated a low-cost system-level implementation of a SRR and readout circuit. Future work that needs to be considered is further sensor optimization to operate within ISM bands for commercialization. We also need to conduct ice sensing experiments in real-world scenarios to validate operation when the environment is uncontrolled. We'd like to acknowledge the NRC, the Department of National Defense, and the Foundation for Innovation for the funding of this research. Additionally, we'd like to acknowledge CMC for the licenses to all the simulation software we've used, and Rogers Corp for supplying the substrates to the devices that the devices were fabricated on. Thank you very much.